When we look at a digital image of a building or a machine part, our human brains automatically see solid, continuous boundaries, but an image sensor sees a grid of discrete values. Zoom in close enough, and solid boundaries dissolve into disconnected, microscopic islands of pixels. We use primary edge detectors, like Sobel or Canny filters, to find structural outlines by calculating sharp changes in light intensity. But these filters only flag individual pixels where the contrast is high. The output is rarely a clean outline. It is a collection of shattered, fragmented lines. This fragmentation is often unavoidable. Real-world lighting is rarely uniform. Camera sensors generate random noise, and objects are frequently obscured by dust, glare, or physical obstructions. To recognize a shape, we have to run a secondary phase called edge linking. This is the computational process of connecting fragmented edge pixels to form logical geometric boundaries. Without edge linking, a computer vision algorithm is effectively looking at noise. It has no way to reason about spatial dimensions of the objects in front of it. We can see the gap between edge detection and edge linking by looking at a standard computer vision test case. This matrix tracks vehicle detection. Panel B shows the raw gradient image. Horizontal lines across the roof and bumper are noisy and broken. Moving to panels E and F, logical operations and morphological thinning connect the disjointed fragments, resulting in unbroken geometric lines. Engineers rely on two distinct methodologies to cross this gap. The first is local neighborhood processing, which operates in spatial coordinates. The second is global parameter mapping, which relies on a mathematical transformation of the data. The choice between these two dictates how the system behaves. One method checks its immediate surroundings, going pixel by pixel, while the other identifies the geometric structure of the entire image at once. In local processing, the logic is straightforward. The algorithm looks at the immediate neighborhood surrounding a known edge pixel to determine if it should be linked to a nearby point. Two conditions must be met. First, the difference in gradient magnitude between a target pixel at xy and a neighbor at st must fall below a threshold. Second, their gradient direction must be similar. Both clear, they link. The system must track, label, and traverse every connected set of points across the grid. On a high-resolution image, this is a heavy computational burden. More importantly, local methods cannot see the global picture. If a line is bisected by a large physical obstruction, the local check runs out of adjacent pixels and the gap remains unbridged. The Hough Transform solves this by abandoning spatial pixel crawling in favor of point-line duality. Consider the Cartesian equation for a spatial line, y equals mx plus c. A fixed slope m and an intercept c define infinite xy points. We plot 3 points here, 1, 2, 2, 3, and 3, 4. By rearranging the equation to isolate c, we get c equals negative xm plus y. In this parameter space, the pixel coordinates x and y act as fixed constants, while m and c become the variables. Now, a single isolated point in spatial space projects as an infinite straight line of possibilities in the parameter space. When two or more disjointed pixels lie on the same straight line in the spatial domain, their projected lines in the parameter space intersect at a single point. This converts the task of finding collinear, disjointed pixels into the simpler task of locating intersection points in a mathematical domain. But the Cartesian version of this transform contains a flaw when dealing with vertical structures. As a line becomes vertical, its slope approaches infinity. This breaks the bounds of the MC parameter space and prevents the algorithm from functioning. To make the algorithm robust across all angles, we must represent the lines using polar coordinates. The polar equation is x cosine theta plus y sine theta equals rho. This tracks the angle, theta, and the perpendicular distance from the origin, rho. In this mapping, an image point projects as a bounded sinusoidal curve. Vertical lines now register at a theta of 0 or 180 degrees, keeping the parameter space bounded and manageable. This polar mapping ensures the algorithm can detect linear structures at any orientation, 360 degrees, without hitting mathematical singularities. Computers detect these intersections using an accumulator cell, a digital grid overlaid on the parameter space, identifying where the highest volume of curves meet. It works through a voting mechanism. As each curve is plotted, every grid cell it passes through has its internal counter incremented.
cells with the highest density of intersections become the brightest points in the matrix. These peaks represent the most likely lines in the original image. This matrix serves as a computational shortcut. It allows the algorithm to ignore the empty space between pixels and identify the points of highest mathematical consensus. We can see this in action on an aerial photograph of an airport. The Canny edge detection in the top right panel is chaotic, with highly fragmented lines defining the runways. When the algorithm maps this noise into a polar accumulator matrix, the spatial gaps are ignored. The scattered pixels along the runway still produce curves that intersect at the same coordinates. Extracting these peaks reconstructs the runways as flawless geometric lines, as seen perfectly superimposed over the physical structure. The Hough Transform proves that when a spatial problem is too noisy to solve locally, translating from pixels to parameters reveals the underlying geometric consensus.
Imagine millions of chaotic, disconnected data points suddenly locking into a rigid geometric grid. That is the core challenge in computer vision, taking a scattered matrix of individual pixels and successfully identifying continuous lines or edges. If a computer tries to check every possible connection between points in high-resolution image space, the combinatorial explosion makes the calculation impossibly slow. Efficient line detection requires inverting our mathematical perspective. The blueprint for this perspective shift exists in these handwritten mathematical proofs, specifically where physical space, x and y, maps to parameter space, m and c. Solving physical computer vision problems requires projecting data into abstract dimensions rather than relying on brute force search algorithms. Looking at this animated diagram of a standard 2D Cartesian coordinate plane, we can see scattered points plotted across an x and y axis. In the context of a digital image, x and y represent the known pixel coordinates provided directly by our data. We represent lines connecting these pixels with the standard linear equation, y equals mx plus c. In this form, a specific slope, m, and a specific y-intercept, c, define one exact continuous line. The limitation is that while we have the x and y data, finding the exact m and c values that connect those pixels requires blind trial and error. As long as we treat x and y as our variables, we remain trapped in physical space, trying to guess the structural constants. To escape that trial and error trap, we execute a mathematical pivot to isolate the constants. We take our standard equation, y equals mx plus c, and algebraically shift the slope term to the other side of the equal sign. Examining the bottom left of these notes, we see the resulting equation tightly boxed, c equals negative mx plus y. This is the foundational engine of our new mathematical space. We must now treat the known pixel coordinates, x and y, as our constants. The structural parameters, m and c, become our independent and depending variables. This creates parameter space, a completely new coordinate system where the axes are m and c instead of x and y. This simple algebraic flip changes the definition of our data. What represents a static location in physical space becomes a continuous function in parameter space. Using a split-screen layout, we can set up a comparative model to translate data from physical image space on the left to abstract parameter space on the right. We start with the first data point, the coordinate 1, 2. Substituting an x value of 1 and a y value of 2 into our new parameter equation generates c equals negative 1m plus 2. Plotting this resulting function onto our new parameter axes creates a continuous straight line. The geometric implication here is that every individual point along this line in parameter space represents a valid, unique line that could pass through the original dot at 1, 2. This is the foundational law of point-line duality. A finite, singular point in physical space manifests as an infinite line of possibilities in parameter space. Returning to the physical space on the left pane, we add our second experimental data point, the coordinate 2, 3. Executing the mathematical substitution for this second point generates the equation c equals negative 2m plus 3. We map this second function into parameter space alongside the first. Notice the precise location where these two parameter lines cross, highlighted here and tagged as m, c. This specific intersection is sketched clearly in the original source material diagram, explicitly pointing to the labeled m, c crossing.
This intersection provides the exact slope and intercept values shared by both of our original pixel points. Finding a line connecting points in physical space is mathematically identical to finding the single intersection of their dual lines in parameter space. We can scale this abstraction up from two isolated points to a dense cluster of collinear pixels, typical in real image data. Translating dozens of collinear pixels into parameter space creates a massive web of intersecting lines. This massive convergence maps directly to the starburst diagram drawn in the foundational notes, showing multiple lines intersecting at a single, dense hub. This convergence creates a computational voting system. Each intersecting line in parameter space casts a mathematical vote for a specific M and C combination. An algorithm simply scans the parameter space, checking for the coordinate that has accumulated the highest number of votes.
The densest intersection point definitively identifies the most prominent continuous feature hidden within the noisy original image. The journey from scattered physical data to abstract mathematical order happens as rigid 2D grids dissolve into flowing cascades of intersecting lines. This geometric inversion is the Hough Transform's bedrock, a pivotal algorithm in computer vision. Because it relies on this accumulating voting architecture, the algorithm is highly robust against missing pixels or digital noise. Instead of impossibly slow point checking, this intersection finding method maps geometry with immense computational speed. Insight in data analysis often emerges by projecting localized information into an entirely new dimension.